Hi guys, today's video is going to be kind of comprising both 3.01 and 3.02, the first two sheets of chapter 15. So I'm going to kind of jump around both of these sheets and just basically introduce the topic of buffers and how we can solve problems that involve buffers. Okay, so first things first, what is a buffer? A buffer is going to be something that contains both a weak acid and its conjugate base. Or we could also make a buffer with something that is a weak base and contains its conjugate acid. Okay, so now both of these things are going to be in a solution of water. Okay, so in number 3 in the 3.01 worksheet, we're given a problem, and in this problem we have 0.5 molar acetic acid and 0.5 molar sodium acetate. In buffers, the conjugate base is going to be given in the solution in the form of a salt. Okay, so the sodium acetate contains that acetate right here. The acetate is the conjugate base of the weak acetic acid that's also in solution. So, to figure out if we have a buffer, basically we have to have some concentration of the weak acid, and we have to have some concentration of the conjugate base, and that's what gives us a buffer. Okay. In number 3, it's asking us to find the pH. To find the pH of a buffer solution, we can use an ice table like this, okay, like we've done in the previous unit. We would set up our initial concentrations like such, do the minus x plus x like we've always done, and eventually set up our Ka expression. When we set up Ka, that's always products over reactants. We end up with 1.8 times 10 to the negative 5, which is the Ka from the problem right here. Okay, and that's going to equal x multiplied by 0.5 plus x, this is from our ice table right here, divided by 0.5 minus x, which came from right there. We do a little math magic. We ignore those x's. Okay, 0.5 divided by 0.5 is just going to be 1. So in reality, the value of x just ends up being 1.8 times 10 to the negative 5th, the same value that was our Ka. We can use that value, take the negative log of that value, because again, x is the hydrogen ion concentration. So if we take the negative log of the hydrogen ion concentration, we can find the pH of this buffer. And we get a pH of 4.74. Okay? This is the old way of finding pH. Okay? Use an ice table, set it up, use Ka, set up that expression, and we can eventually get there. There's an easier way that we can do this as well. So if I wanted to find the pH of a buffer, we have an equation for that. The equation is called the Henderson-Hasselbalch equation. So I can use this to solve for the pH as well. So in this scenario, what I would need to do is I would need to find my pKa. Up above, we still have the Ka is given to us as 1.8 times 10 to the negative 5. So if we take the negative log of Ka, that's going to equal pKa. So let's take the negative log of the 1.8 times 10 to the negative 5, and we get an answer of 4.74. Okay, we can use that pKa in our Henderson-Hasselbalch equation. So we're going to plug that in, and I will have pH equals 4.74 plus the log of my concentrations. Now, in my original setup of this expression, we have A1 minus and we have HA. HA just represents a generic weak acid, some weak acid. And A1 minus represents a generic conjugate base, or in other words, some conjugate base from my buffer. So up above, we were given that we have a concentration or a molarity of both of these things that equal 0.5. So I can plug in 0.5 for the conjugate base, which is the acetate. And I can plug in 0.5 for the weak acid, which is the acetic acid. So let's plug that in. So I have the log of 0.5 divided by 0.5. Now that equals 1, and the log of 1 actually equals 0. So in other words, using this Henderson-Hasselbalch equation, we can solve for pH as well instead of using an ice table. Okay? Now, you can only use this Henderson-Hasselbalch equation if you have a buffer. A buffer is when you have a weak acid and its conjugate base both in solution. If you don't have both of those things in solution, you don't have a buffer, and you can't use Henderson-Hasselbalch. Okay? So our final answer here using this equation is just going to be the exact same, 4.74. So let's continue on then. Something else that comes up with buffers is they're supposed to be resistant to pH change, meaning if I add some strong acid or some strong base to my buffer, it should be able to neutralize that. That's the whole point of what a buffer does. So, if I use the buffer from question number 3 on 3.01, and let's say I add some strong base to that. Okay? Now, the strong base I add could be something like NaOH. Alright? In my reaction in red up above, I don't include the sodium, because in reality that sodium ion is just going to be a spectator. So if I actually wrote this out, I would have Na1 plus OH1 minus, and then I would also have my acid from the buffer, which is acetic acid in this case. And then those things would react. When they react, I get water, and I would get sodium ions and acetate ions, because that's really salt, but it's salt that dissolves, so that's going to be a dissociated solution. Okay? So, when I add strong base, I don't need to include the cation, that sodium piece, because it's really just going to be a spectator, and it's going to get crossed off anyway. And if you look, then I'm just left with exactly what I have up above. Okay? So you add base to this buffer, strong base to this buffer, and the acid inside that buffer will neutralize it, giving us water and the conjugate base back. On the reverse of that, let's say I add acid to my buffer. Now when I add acid, again, it's a strong acid, so in reality I'm adding something like HCl. But that chloride that comes from HCl is just going to be a spectator, much like the sodium from sodium hydroxide was a spectator. So I can kind of ignore it and skip that step and just don't even put it in the reaction because it's not going to do anything. So now I add strong acid to my buffer, and it's going to be the base inside my buffer that neutralizes that acid. So the base in my buffer in this problem is the acetate ion. So I end up with that acetate neutralizing that strong acid, which is H1+, and that gives me back my acetic acid. So recapping 3.01, essentially, in order to get a buffer, you need a weak acid and its conjugate base both in solution at the same time. Or you could also make a buffer with weak base and its conjugate acid in solution at the same time. And the purpose of buffers, or what they do, is they resist change in pH. Okay, so when you add a strong acid or a strong base to a buffer, it's supposed to be able to neutralize that strong acid or strong base and keep its pH very close to where it started. So in question number 8, we're going to have an example of how do we calculate pH after we've added either some acid or some base to our buffer. Okay, so in number 8, we're going to add 0.01 moles of solid sodium hydroxide to this buffer from problem number 3. In order to calculate how much of this gets neutralized, we're going to use something new. We're going to use what's called a MINE table. MINE is going to stand for moles initial, that's the MI. neutralized moles, which is N, and then end moles, or moles after the neutralization has occurred at the very end. Okay? So in this problem, we're adding base, strong base. What in our buffer is going to react with that? It's going to be the acid of our buffer. The acid inside our buffer here is acetic acid. Inside a MINE table, we have to use moles for the numbers. In ICE tables, which we've used previously, we use molarity. But in MINE tables, we have to use moles. The buffer we have is 1 liter, which is very convenient, because then we can simply take our molarities, and the quantity of moles is going to be the exact same. So we set up a MINE table kind of like an ICE table. We have our initial values up top. We have 0.50 moles for the acetic acid. We have 0.01 moles for the sodium hydroxide. And then we have 0.5 moles for the acetate as well. What's different is in a MINE table, these are for neutralization reactions only. So neutralization reactions will go until completion, until something runs out. In other words, which of these two initial quantities is smaller, all of the smaller one is going to be used up. So 0.01 is obviously smaller than 0.5. We use up all of that strong base, and we neutralize it with the acetic acid inside our buffer. At the very end, we end up with 0.49 moles of acetic acid, and we end up with 0.51 moles of acetate. So at this point, we have one of two options to solve for pH. You could take these values of moles, and we could set up an ICE table. We could set up an ICE table using the Ka of acetic acid, the dissociation reaction of acetic acid, plug in these concentrations, and solve for X, and then take the negative log of X to solve for the pH once you're all done with that. That's kind of a pain in the butt, so we're not going to do that. We can make it easier. We can take this 0.49 moles of acetic acid and this 0.51 moles of acetate, and we can plug it into the Henderson-Hasselbalch equation because we still have a buffer. If you've got weak acid and conjugate base, you've got a buffer. So we don't have to do an ICE table. We can make this much easier. So let's take the information from that problem. The Henderson-Hasselbalch equation is written up above, right here. And we're going to take that 0.51 moles, or molarity, of the conjugate base, the acetate, and we're going to take the 0.49 molarity of the acetic acid that we have left over, and we're going to plug them into our Henderson-Hasselbalch equation. The Ka of acetic acid is 1.8 times 10 to the negative 5. That's something you could look up in the book. You take the negative log of that Ka, and you get the pKa, which is 4.74. We take that pKa and we plug it in. So our final expression is going to look like this. pH is going to equal 4.74 plus the log of 0.51, which is the acetic acid, or I'm sorry, the acetate, divided by 0.49, which is the acetic acid. You solve that, plug in your calculator, and you get a final pH of 4.76, and this is after that base that we added has been neutralized. So using the Henderson-Hasselbalch equation with buffers, we can solve for a couple different things. The previous problem, we just solved for pH of a buffer after we've neutralized some strong base that got added. We can also use the Henderson-Hasselbalch equation to create a buffer at a very specific pH. So this problem is the one about 2/3 of the way down on the 3.02 worksheet, asking about how many grams of sodium acetate we would need to add to a 0.333 molar solution of acetic acid in order to create a buffer with a specific pH of 5.14. So we can set this up using, again, the Henderson-Hasselbalch equation, but now the pieces of information we have are the pH, which was given to us, the pKa, which for acetic acid is 4.74, which we can look up from the Ka in the back of the book and solve for. And then in the log portion of this expression, we don't know what the conjugate base is, because it's not given to us, but we do know the concentration of the acid, because that's given to us in the problem. So really, we have this expression, and we only have one piece that we don't know, the conjugate base concentration. We can subtract 4.7 from both sides of our expression, and we end up with 0.04 equals the log of A1 minus divided by 0.333. To get rid of a log, mathematically, we have to take 10 to the power of both sides. that 10 to the power of log will cancel out, and we end up with, on the left side, 10 to the 0.4, and on the right side we just end up with A1 minus, which is the conjugate base, divided by 0.333. We do a little algebra, and we can get a concentration of A1 minus equal to 0.84 molar. Now, what we actually solve for, because this is acetic acid and acetate, we solved for the acetate concentration. But in the problem, it's asking us how many grams of sodium acetate do we need. So in reality, we have to get back to the concentration of the original sodium acetate. Sodium acetate is a salt. Salts that dissolve dissociate 100%. In other words, the concentration of this ion, any of the ions that came from that salt, are going to be exactly the same concentration as the salt originally had. So we're going to use this 0.84 molar for our concentration of sodium acetate as well. In the problem, it tells us that we have 0.750 liters, or in other words, 750 milliliters, I think is what it says. So we have 750 milliliters. We're going to change that to liters so we can use it. We're going to use factor label, including the molarity of our sodium acetate, which we just solved for using Henderson-Hasselbalch, 0.84 moles per 1 liter. The next factor, we got to get to grams of salt of the sodium acetate that we need, so we use the molar mass off of the periodic table, which is 82.03 grams per 1 mole. After we do all that math, we end up with a total mass of salt that needs to get added equal to 52 grams. So these are a couple of the intro topics that we can use for buffers. We can use the HH, or the Henderson-Hasselbalch equation, to help us solve for the pH of a buffer. When we add either strong acid or strong base to that buffer, we can use a Mine table and solve for how much of that acid or base gets neutralized by the buffer, and then use the new values of the weak acid and its conjugate base that are left over and solve for pH using the Henderson-Hasselbalch equation. But we can also create buffers at very specific pHs like we did in this last problem. I can give you a pH and give you what you're making the buffer out of, for example, acetic acid and sodium acetate, and you can solve for exactly how much of either of those two things we need in order to create this buffer at that specific pH.